Okay, gluconeogenesis. So today might be one of the hardest days of the block. So I've requested seat belts to buckle in. Because making sugar sounds like it's easy. And it is. But the difference, what we're going to be looking at primarily is regulation. Because the regulation, we got to make a major metabolic shift in order to make glucose from our normal metabolism in liver. So let's look at our chart and see where gluconeogenesis comes in. Here is our normal fasting state. Here's our mealtime. Here's our recovery back to our normal physiological state. Now, this is the point that we started looking at yesterday. And this is where glucagon signaling comes in and insulin drops down, because now we are in a fasting state, and this is where we have to start supplying glucose to the circulation in order to maintain glucose levels. Because remember, if we don't do that, we end up down here because we have continuous glucose transporter utilization that can work under all plasma concentrations of glucose. So the key is, when does glycogenolysis start? So glycogenolysis, remember, is triggered by glucagon activation in the liver. So as soon as insulin levels start to drop because of dropping glucose levels, glucagon levels start coming up. So at this time right here is when glycogenolysis is going to start. And so glycogenolysis is going to be our first line defense against falling plasma glucose levels. So at this point, we can say this is when glycogenolysis starts, and then glycogenolysis ends. Now, this is going to end because we have a limited store of glycogen in our liver. Now, at the same time, we also saw that fats were being released from adipose tissue based on glucagon signaling. So that means fats are also being released at this point. The fats turn out to be our secondary source of energy because glucose is readily available in glycogen stores. All we have to do is just a couple of biochemical steps and the glucose gets out into the circulation and appears instantly. Fats, we have to release from fat tissue, travel in the circulation, get to the liver and muscle, get it in through the carnitine transporter, then go through all the oxidative reactions in order to generate energy. So even though that we have fats being released here at the same time as glucose in glycogen stores, it just takes that much longer for fats to be able to supply energy. Okay, so that's why we have the fat release here. So the energy that fats are providing is going to compensate for the reduction in glycogen over time. Now, fat hydrolysis is good for most tissues except the brain. So that means that as glycogen levels are starting to drop, we still need some way of maintaining our glucose level for our GLUT3 and GLUT1 transporters. So right here, again, same point, this is where gluconeogenesis is going to start. Now the contribution of gluconeogenesis to maintaining carbohydrate levels is going to be like that. It's slow to start. The reason it's slow to start is because we have to get the precursors, the substrates for making glucose, we have to get them to the liver, and then the liver has to go through all of the metabolic steps to make glucose. But the gluconeogenesis is our backup to glycogen. So everything is starting right here at this point. It's just the timing of when these products become available and supporting this glucose level. Now, What we're talking about here is gluconeogenesis starts in the fasting state. And then when we get out to a point, if we break this out, so this is approximately, if this is what we're saying is 90 minutes over here, we're talking this point here might be out to 24 hours. Now, if we have a little bit of a time break here, and now we start with 2 days out to say 20 days, this range in here, 2 days to 20 days, is called starvation. So we go beyond the fasting state. So where are we most of the time? Most of the time we are in either a fed state or a postprandial state. So that we're past our eating time, we're in a fasting state, we go for 6-8 hours maybe maximum, and then we eat again and we boost back into the fed state. But if we don't eat and we start going past this, say in a fast, our glycogen stores will be completely gone, and gluconeogenesis will be our only source of glucose in our body. Okay, so why is this information so important? There are many test questions, both in our block database and the NBME and the Step 1 exam, that are asking you, what is your source of energy after a certain time? So if an individual is exercising and they're 24 hours into a fast, what is their primary energy source? The energy source for glucose will be gluconeogenesis and fatty acid oxidation. Okay? Now, fatty acid oxidation is not going to work for the brain, so the glucose we need for the brain. But as we get out to the 2-day point, what we're going to see is we're going to see a drop in gluconeogenesis. This drop right here is called a glucose sparing response. Because glucose is very expensive to make and you need a lot of substrate to make it. We'll take a look at those. So what compensates for the drop in glucose? Because your brain still needs glucose.
Ketones.
Ketones, yeah. So this level here is made up by ketones. And we'll talk about that later in this morning, which is ketogenesis. Okay, so the ketones are a very, very powerful energy substrate for the brain and muscle. I like to call muscle a goat. It'll eat anything. It uses glucose, it uses fats, it uses ketones, it uses acetate. It'll use anything to generate energy. Okay, so now, that's kind of the pattern, and that sets us up for moving further along in the fasting state, because the initial fasting state is glycogenolysis. Now we'll move on and we'll look at gluconeogenesis, and then we'll move a little further on more into a starvation state and looking at ketones. So the sources, let's look at the sources of the substrates for gluconeogenesis. Now, gluconeogenesis, 90% of gluconeogenesis is done in the liver. 10% is the kidney. Now, this is a whole body ratio of gluconeogenic activity, but this is what we're considering. The 90% in the liver is really physiologically the only thing you have to think about. So the first source of substrate is going to be lactate. So lactate is coming from red blood cells and skeletal muscle in an anaerobic state. We are going to be taking up the lactate in the liver, and the liver is going to use lactate dehydrogenase to convert that into pyruvate. Okay? So we saw this reaction a lot in muscle and red blood cells because there we want to move the pyruvate out in anaerobic respiration to generate lactate. And the reason the LDH went the other way is because we had high concentrations of pyruvate in those cell types, and that's going to push the reaction toward lactate. Now we have a high concentration of lactate going into the liver, and so the LDH is going to be operating in the other direction to generate pyruvate. The other substrate is alanine. Alanine is primarily coming from skeletal muscle because our largest store of protein and amino acid in the body is skeletal muscle. Now, why is skeletal muscle giving up an amino acid? Well, this is part of what we're going to talk about tomorrow when we're getting into amino acid metabolism. We're getting further along in our fasting starvation state. So now what we're going to do is we're going to capitalize on amino acids generating energy. So skeletal muscle will put out quite a bit of alanine. The liver picks this up. And our liver biomarker, alanine transaminase, we'll look at this more tomorrow, is going to convert this into pyruvate. So this is a one-step reaction. We'll see this tomorrow when we talk about nitrogen balance. But simply what we're going to do is we're going to take the nitrogen off of alanine and have only the carbon backbone of alanine amino acid left. That carbon backbone is actually pyruvate. Now the final source of substrate is glycerol. And where does glycerol come from in the fasting state?
Is it DHEP?
No, it's not DHAP. But it's a good, think about this, because if it was DHAP, that would mean that glycolysis is working in the liver.
Yeah.
And so this is where it's important to make sure that you've got your physiological states in order to be able to see these pathways. So glycerol is coming not from the liver, it's coming from another source. Adipose fat. So glucagon signaling right back here at this start is inducing fatty acid hydrolysis off of triglycerides. If we cleave off 3 fatty acids off of triglyceride, we're left with glycerol. The glycerol has nowhere to go except the fatty tissue secretes that into the blood. The liver takes up the glycerol. And then the glycerol magically becomes DHAP. Now how does that happen? We have a 2-step reaction. Glycerol, 3-phosphate, by an enzyme called triose kinase or glycerol kinase. And then this reaction is glycerol 3-phosphate dehydrogenase reaction. So the glycerol now is forming DHAP, not pyruvate. Pyruvate we're going to process in a second, and that's a more complicated direction to go. But DHAP is a glycolytic intermediate. So that tells you that if this is a substrate for gluconeogenesis going into glycolysis, we're going to take advantage of going backwards in glycolysis. That is gluconeogenesis. Now, it's not that simple because there are several irreversible reactions that we have to get around, and that's where we're going to have to take some bypasses, and that's where diseases can occur. Again, points of regulation. Yes?
Can you repeat the enzyme that takes glycerol to G3P?
Yeah, this is, sometimes it's called triose kinase.
Okay. Thank you.
The more common name for this is glycerol kinase.
Are both enzyme names used interchangeably on exams?
Actually, I prefer glycerol kinase. The triose kinase I probably wouldn't use. Some textbooks, some biochemistry textbooks use that old terminology. But best it's called glycerol kinase.
Thank you.
Okay, so these are our three major precursors, and I'll show you some points of entry of other precursors and substrates as we move along. So let's start with pyruvate. Now pyruvate has two directions that it could possibly go in the liver. One is to form lactate. But we know this direction is not going to happen. And the reason it's not going to happen is because we have high concentrations of lactate, and so the LDH enzyme, lactate dehydrogenase, is going to be pushed in one direction. So the flow of substrate will definitely not go backwards. So pyruvate then only has one direction, and that is to enter the mitochondria. Okay, so now, before we go into gluconeogenesis, let's review the first steps of TCA. So pyruvate, by pyruvate dehydrogenase, is converted into acetyl-CoA, and then the acetyl-CoA is condensed with oxaloacetate. To make citrate. Now this is the normal path in the fed state. In the fed state, of course, as our energy charge rises, the citrate can be used for fatty acid synthesis. But now in the fed state, we have a completely different metabolic activity. The pyruvate is going to be converted into oxaloacetate. And this is fasting, and this enzyme is called pyruvate carboxylase. So I like to look at this as kind of a pendulum swinging back and forth. We're going to go down the path of PDH in the fed state. We're going to go down pyruvate carboxylase in the fasting state. Now, what determines the direction of pyruvate? This is going to be the levels, the concentration of acetyl-CoA. Acetyl-CoA, remember, activates the PDH kinase. And if we activate that kinase, this is going to phosphorylate PDH and make PDH inactive. If we make PDH inactive, because of the rising concentration of acetyl-CoA, the acetyl-CoA is actually an activator of pyruvate carboxylase. So the concentration of acetyl-CoA in the matrix of the mitochondria is the determining factor if pyruvate will be converted into more acetyl-CoA or if it will be shunted into oxaloacetate. So that means the concentration of acetyl-CoA will dictate if we go into gluconeogenesis or not. So what determines the concentration of acetyl-CoA? Well, In the fed state, acetyl-CoA is coming down the pipe from glycolysis. We have citrate in the fed state disappearing very rapidly to make a fatty acid. That means that the acetyl-CoA is uninhibited from moving in this direction. Okay? Now, as our acetyl-CoA levels start to rise, we are essentially saturating the TCA cycle. So everything is going to start to slow down on the TCA cycle, and we are going to start building up our acetyl-CoA. Once that starts building up the acetyl-CoA, we have our PDH shift to pyruvate carboxylase. So in the fasting state, glycolysis is not working in the liver because we got to go backwards. So we're going to shut down glycolysis, but yet we have an incredibly high concentration of acetyl-CoA to shift this direction of pyruvate. What's contributing to acetyl-CoA in the fasting state in the liver? Fats, beta oxidation, yeah. Now this is a little bit of a paradoxical idea, but the concentration of energy in the mitochondria of the liver is at its highest in the fasting state, not in the fed state. So the concentration of acetyl-CoA is incredibly high because as we oxidize these fatty acids coming from adipose tissue, because we have coordinated glucagon signaling, we are going to increase the concentration of acetyl-CoA through the roof. So that inhibits PDA, it activates pyruvate carboxylase. So now the pyruvate that has come from lactate and alanine are pushed into oxaloacetate. Now the oxaloacetate, this is a simple redox reaction. Normally we go that way, malate to oxaloacetate in the TCA cycle. That's not going to be possible in the gluconeogenic fasting state because we have a high concentration of oxaloacetate from this direction and a low concentration of malate, because malate is going to exit the mitochondria. And so that is going to make sure that we keep pushing this in the opposite direction of the TCA cycle. Now, once we get malate into the cytoplasm, we're going to convert this back to oxaloacetate. And there's an important reason why we bypass sending oxaloacetate out, and that's because we are bringing some of that rich energy charge from the matrix of the mitochondria out into the cytoplasm in the form of NADH, which we're going to need for gluconeogenesis. Now, the next step from oxaloacetate is going to form phosphoenol pyruvate, PEP. The enzyme that does this is phosphoenol pyruvate carboxykinase. There's another enzyme that you got to know. This is a wonderful target for anti-diabetic drugs. Why is that such a wonderful target for anti-diabetic drugs? It stops gluconeogenesis. So what you're doing here is trying to control glucose levels from the digestive dietary source by reducing the amount of glucose intake, and you have a way of slowing down endogenous production of glucose, which will exacerbate the problem. So this enzyme is one of the targets for that drug, metformin. So metformin is your first-line anti-diabetic drug. Somebody starts developing pre-diabetes, you get them on metformin. Now metformin has been shown to have additional metabolic effects that can help control glucose levels, but this is one of the first levels it hits. So you can see that metformin is a very, very mild anti-diabetic drug. You're not affecting the insulin receptor activity. All you're doing is just slowing down the amount of glucose the individual's making so you don't continually add to the problem. So now, phosphoenolpyruvate. Remember that this is the last step in glycolysis. We can take PEP and turn it into pyruvate. But that's an unproductive reaction for gluconeogenesis, because all we're going to do is this loop around. So this enzyme that does this reaction is pyruvate kinase. This is one of our ATP generating enzymes, but we need to shut this enzyme off. And so glucagon signaling in the liver activates the sequence of reactions and signaling to take it down to activate protein kinase A. We saw yesterday that protein kinase A, one of its first effects, was to help activate glycogen phosphorylase. It also has another effect to phosphorylate pyruvate kinase, and that makes this enzyme inactive and prevents the conversion of PEP to pyruvate. Now, once we get to PEP, now all of these reactions in glycolysis are reversible all the way back up to PFK1. So we're simply going to just reverse the reactions in glycolysis. When we get to PFK1, we have another problem here. So we have to find a way to control that enzyme to get around that problem. The NADH that is coming out of the mitochondria is going to be supplying an important step to reverse glycolysis. Remember that enzyme? This one here is glyceraldehyde 3-phosphate dehydrogenase. So this is a redox enzyme that produces NADH in glycolysis. So if we're going to reverse that enzyme, we're going to need to supply it with NADH to go backwards, otherwise it'll get stuck. The NADH has to come from the matrix of the mitochondria because glycolysis that generates NADH is shut down because we're going backwards. Okay? So we're trundling back up our substrates, up glycolysis backwards. Now when we get to PFK1, oh wow, look at that, we're already on page 8. Now when we get to PFK1, we have a bit of a problem. Yes?
Glyceraldehyde 3-phosphate dehydrogenase, which step does that catalyze?
That is a step that takes glyceraldehyde 3-phosphate into 1,3-bisphosphoglycerate. That's the normal step. That's the normal glycolytic path. what we're going to do is we're going to take the 1,3-phosphoglycerate and turn it back into glyceraldehyde 3-phosphate. And so the dehydrogenase enzyme is going backwards, so you're not making NADH like in glycolysis, you're going to consume it in order to go backwards. Right.
So is that the enzyme that you think is most important between phosphoenolpyruvate and fructose 1,6-bisphosphate?
Yes,
Okay.
exactly. That's one of those, I call those funky trick questions, because it's so subtle. It's like, whoa, wait, NADH? But it's not the type of question that I would ask, but it's definitely the type of question that a step 1 writer might ask, because it requires a very detailed, intimate knowledge of gluconeogenesis, way beyond what medicine justifies. But, you know, the step 1 is this rite of passage and punishment thing, right? Yay! Okay, so PFK1. PFK1 is going to catalyze the reaction of fructose (6-phosphate) to fructose 1,6-bisphosphate. So this is the normal glycolysis direction. Now the problem with this reaction is that we are using ATP in this reaction. So that makes the forward reaction of PFK1 going from fructose 6 to fructose 1,6 irreversible. So this enzyme, we cannot reverse this. We cannot go backwards. So this, very much like pyruvate kinase, we have to find a way around that enzyme. So the enzyme we're going to use is fructose 1,6-bisphosphatase. Fructose 1,6-bisphosphatase. And what this enzyme is going to do is it's going to remove the phosphate group from the number 1 carbon of fructose to give us fructose 6-phosphate. Now here's our problem. The forward reaction of PFK1 is a very powerful reaction because we're using ATP. So we got a lot of energy going into that reaction. We need to continue going backwards in glycolysis for glucose production. So we have to find a way to prevent the normal reaction, to prevent this loop, an unproductive loop. So that means we have to regulate PFK1. Now, the first thing that's going to regulate PFK1 is something you already know. ATP. What is our ATP? Then again, this is that paradoxical thought. What is the ATP level in the hepatocyte in the fasting, even starvation state? It's really high, incredibly high, because we've got so much beta oxidation going on from fatty acids that we have a lot of energy substrate in there. So if we're not using that material to push into gluconeogenesis, we can keep our ATP concentration exceptionally high. But gluconeogenesis is so important that the inhibition of this enzyme by ATP is incomplete and not enough. It's not good enough. So therefore, we have another regulation. And somebody mentioned this, I recall, when we were talking about glycolysis. Somebody mentioned, isn't fructose 2,6-bisphosphate an activator of PFK1? Yes, it is. This compound is able to activate PFK1. this also inhibits the bisphosphatase. So now under fed conditions, we're going to flip back here, fed conditions, we've got glycolysis running. What we're going to do is we are going to take a little bit of a side reaction right here. We're going to take a little bit of fructose 6-phosphate, not a lot, just a little bit for making a regulator. We're going to take it out of the glycolytic flow, and we are going to use phosphofructokinase 2 to convert a little bit of the fructose 6 into fructose 2,6. Now in glycolysis, in the fed state, that is going to generate an activator for PFK1. So that allows us to accelerate PFK1 in glycolysis in the fed state. It also allows us to inhibit the phosphatase in the fed state in glycolysis to prevent going backwards, so we can make sure we got flow going in the right direction. Now let's get to the fasting state. Glycolysis needs to be shut off. We need to go backwards. So that means we need to remove the fructose 2,6 bisphosphate from our reaction. So how do we remove that? What we're going to do is we are going to convert the fructose 2,6 bisphosphate back to fructose 6-phosphate. And we're going to do this by PFK2. Okay? Now, PFK2 has two activities. In the forward direction, it has kinase activity. So it can convert fructose 6 into fructose 2,6. In the reverse direction, it has phosphatase activity. So that's going to remove this number 2 phosphate as inorganic phosphate to return fructose 6-phosphate to the pathway. Okay, so now that means we have a regulation point of the kinase versus phosphatase activity. Here's where our master hormone is controlling everything. So glucagon is going to activate protein kinase A through its normal signal transduction. And the pKa is going to phosphorylate the PFK2. And when it does, it activates the phosphatase activity and inhibits the kinase activity. Does your brain feel like cottage cheese yet?
Could you repeat that?
Absolutely. So let me repeat this in both states. We'll go in both directions. Maybe that'll help. That'll clarify. So in the fed state, let's start with the easy one. Fed state, glycolysis running through. We want to convert fructose 6-phosphate into fructose 1,6. That means we want PFK1 active. We want the fructose 1,6 bisphosphatase inactive. In order to do that, we are going to have increasing amounts of AMP in the fed state because our energy charge is going down. So that's going to activate PFK1. And we also want a little bit of fructose 2,6 bisphosphate because this is an allosteric activator of PFK1. So in the fed state, we have no phosphorylation on PFK2. Without phosphorylation, the kinase activity is active. If this is active, that means we can make our fructose 2,6. Make our activator activate PFK1 to make sure that glycolysis is running. In the fasting state, we want to make glucose. So now we have to inhibit PFK1 to prevent this direction. We need to activate the phosphatase so we can go around this block. So now glucagon signaling is going to phosphorylate the PFK2. Once we phosphorylate the PFK2, the kinase activity is inhibited, the phosphatase activity is activated, and so now the fructose 2,6-bisphosphate is converted back into fructose 6-phosphate. What this does is it reduces the concentration of fructose 2,6, the activator. So we're taking the activator away from PFK1, and we're also taking the inhibitor away from the bisphosphatase. So we're shutting down PFK1 and we're activating the phosphatase enzyme. Okay? And all of this is simply controlled by glucagon signaling. Yes?
So is that like little side note up top how PFK2 gets phosphorylated to go backwards? Is that all that is?
Yeah.
Okay.
So this is how PFK2 becomes phosphorylated because of glucagon signaling, because we're in the fasting state. Yeah.
Does insulin do the flip where it takes off?
Perfect. Excellent. Insulin will activate what type of enzyme? A phosphatase.
Oh.
Wait.
I got it.
See, you checked out for approximately 7 seconds.
My world changed.
And the whole world changed, right? So insulin will activate a phosphatase to remove that phosphate group to reactivate the kinase activity of PFK2.
Do we have to know the name of that phosphatase?
No. It's an insulin-dependent phosphatase. There's a bunch of those. This is one of the most wicked points in biochemistry. The conversion of a fed state to fasting in the liver. Remember earlier in the block I was telling you the liver is just so much fun. It's like, right. Okay, so now, we good with that before we move on? Okay, so we're at fructose 6-phosphate. We've done all of this nastiness to get around that PFK1 problem. And so now we are going to convert this to glucose 6-phosphate. And remember, glucose 6-phosphate has 3 directions it can go. The direction we want to go in is this. We want to convert the glucose into glucose 6-phosphate simply because we want to be able to transport this out of the liver into the circulation using GLUT2. So the enzyme that does this is glucose 6-phosphate, 6-phosphatase, glucose 6-phosphatase. This is another one of those tricky type of questions. This reaction from glucose 6-phosphate to glucose is specific for the liver, and skeletal muscle can't perform this reaction. Why?
Skeletal muscle doesn't need
muscle doesn't want to give it away.
Exactly. It doesn't need it, but why doesn't it do this reaction? Why does only the liver do this reaction? It's a very simple answer right in front of you. I know it's kind of
Wouldn't be able to trap the glucose coming in.
There's no receptor.
There's no
State.
There's no enzyme.
no enzyme. That's what I mean. It's a very simple answer, but that is a trick question that comes up. Came up on the MBME final last year for everybody. And I put that in there.
What was that question again?
So the conversion of glucose 6-phosphate to glucose only occurs in the liver and no other cell type. Why is that? Because the liver is the only one that has glucose 6-phosphatase enzyme. Again, it's one of those stupid little trick questions. Now, why doesn't this reaction occur? Once you convert it back to glucose, why doesn't glucokinase do this loop? What is a regulator of glucokinase? Yeah. It's a weak regulator, but as you increase the concentration of the product of this reaction, this is going to slow the activity of this. And just by that simple inhibition, once you make glucose, you're making so much glucose that you're going to reverse that transporter, send this out into the circulation, and now you've got a big gradient of glucose, which is high inside the cell and low outside.
So you want to draw the arrow the other way, right?
Yes, so this direction,
Not the,
No, not that arrow, the other
so the
one.
next thing, glucose next to cellular.
this one here.
And that's
The one
next to
just
the-
to the
High
To the left,
glucose
just
inside
arrow
the
up.
cell.
Wow, thank you. Dehydrogenase. And what controls that enzyme?
NAD levels.
NAD?
pH.
pH. So elevated concentrations of NADPH will inhibit this direction. What's the NADPH level in the liver in a fasting state? It's pretty high. Again, this is one of those counterintuitive things. This is a biosynthetic reducing power. We're not performing biosynthesis. So what's going on here? Well, as soon as you have a little glucose 6-phosphate, it's going to enter this pathway regardless of the fed or fasting state. But as soon as you increase your NADPH levels high enough, you block any further movement of that substrate into this direction. How quickly will you fill up your NADPH levels? Pretty fast, right? Because you're not using any of it, because you're in a fasting state. The only way you're going to use this is if you're making what two molecules?
Superoxides. Right. Free radicals.
Free radical, I wasn't going there, but you're right. Of oxidative damage, you'll use it there. But what are the biosynthetic molecules you're going to use? Fatty acids and? Huh. What's the other lipid?
Cholesterol.
Cholesterol, right. So cholesterol and fatty acids are not going to be made in a fasting state. So that means your NADPH levels, once you make them, they're going to stay high. You're not going to get rid of those. Now let's push the envelope on you a little harder. In the fasting state, why can you not make fatty acids and cholesterol? What is shut off and controlled?
Carnitine.
Carnitine transporters actually, is it active or inactive?
Oh, it's active.
It's active, right, because your malonyl CoA levels are low, which is the inhibitor, and you want fatty acids coming in there. Somebody said ACC?
Yes.
Acetyl-CoA carboxylase. What controls that enzyme?
Glucagon.
insulin and glucagon. So glucagon, again, will phosphorylate that enzyme and turn it off, so you block movement into fatty acid synthesis. And by default, you block into cholesterol synthesis. Okay? Insulin will dephosphorylate that enzyme to put you in the fed state to make fatty acids. Again, top of the pyramid, insulin and glucagon signaling. So this is why I mentioned at the beginning today of making concept maps for fed and fasting state. So then you don't have to go back and forth in your thinking. You can think, okay, this particular question is asking me something about the fed state. Fed state means lots of glucose, lots of insulin. I'm in the liver. What's going to happen? And so you've just completely polarized your thinking down into one channel. Another question might be, fasting state, glucagon levels are high, adipose tissue. What's going to happen here? Because if you go back and forth too much from the fed and fasting state, I mean, you can do this, but it takes a lot of mastery and time to do this. Then what's going to happen is you're going to stop and you're going to look upstream and downstream of these pathways and you're going to lose your way. Where am I in these pathways, and what state and what organ?